Now, see, hopefully this is the last question of your electrochemistry. So let's do some problem. See, the specific conductance of saturated AgCl solution is this, and that of water. Obviously, that water in which the solution is prepared. So this is the blank reading, or you can say controlled reading. So of water alone is this, and lambda m infinite for AgCl is given this. Find the solubility and solubility product for AgCl. So first of all, in this question, you have to find out what is the molar specific conductance means kappa for AgCl only, right? So this is equal to kappa of AgCl solution, saturated solution, minus kappa of what? Water, right? So kappa of AgCl solution is 1.86 into 10 to the power minus 6 minus 8, no, 6 into 10 power minus 8. So this is equal to, now you can write 1.8 into 10 power minus 6. Ohm inverse centimeter inverse, right? So you have calculated kappa for AgCl. Now see the formula. What formula I have told you, that the molar conductance of AgCl at particular concentration, this you can take equal to infinite for AgCl. Why we can take this? Because you know, in the saturated solution, whatsoever the maximum quantity of AgCl that can be converted into the corresponding ions, that is fixed at given temperature. No more than that salt can be dissolved. So this is the definition of what solubility and solubility product. So this we can take, this is equal to kappa of AgCl alone, not with water, multiplied by 1000 divided by what? You can take molarity. So in place of molarity, you can take solubility, S. So solubility is equal to, solubility of AgCl is equal to kappa 1.8 into 10 to the power minus 6 into 1000 divided by, I think I'll have the same unit, so there is no problem, 137.2, right? So you will get, this is equal to what? 1.3 into 10 power 10 to the power minus 5 moles per liter. Moles per liter, right? So I mean solubility of AgCl, we have calculated this, and you know, solubility of AgCl, solubility of AgCl is equal to, you can write concentration of Ag plus is equal to the concentration of Cl minus, because there is no change, there is no complex formation, no hydrolysis, nothing is happening in this solution. So this relation is always valid, right? So Ksp of AgCl is equal to concentration of Ag plus in the saturated solution, concentration of Cl minus. So you can write here 1.3 into 10 power minus 5 into 1.3 into 10 power minus 5. So this is equal to 1.7 into 10 to the power minus 10. And if the solubility in moles per liter, then there is no need to specify the unit of solubility product. And this is the solubility product of AgCl, and this is I mean very close to the experimental value, right? This is very close to the experimental value. So if this type of question is asked, you can very easily answer this question, right? And there are some other relations, like what is relation between ionic mobility and molar conductance, what is transport number, although these are not directly mentioned in your syllabus, but I am giving you some formula. So if somebody asks, then you can answer those questions as well. And after that, we will see some conductometric titration graphs, right? Now, see the relation between equivalent conductance. Actually, equivalent conductance is more convenient for us, milli equivalence concept over mole concept. In general terminology, equivalent conductance can be termed as a ionic conductance, but molar conductance you cannot say the directly ionic conductance, and ionic mobility, right? So, see, ionic mobility, it is ionic mobility. It is represented by U, right? So, and equivalent conductance, all of you are knowing, it is lambda EQ. Equivalent conductance or ionic conductance, it is represented by lambda EQ, right? Okay, suppose that we have electrolyte AB, simple electrolyte, at infinite dilution. This is completely converted into A plus and B minus. This is nil, and this is 1 mole at infinite dilution. At infinite dilution, right? Okay. Now see this equivalent conductance of anion and cation, because at infinite dilution both ions behaves independently regarding their conduction of electricity. Means you cannot complement both of them, that total current carried out by cation is equal to the total current. No, both were independently contribute in the conduction. So you can write here lambda equivalent. I am talking about at infinite dilution, lambda equivalent of cation, C for cation here, right? Equivalent, I am writing equivalent here, is directly proportional to the ionic mobility of cation, UC. Means more the this equivalent conductance for the cation, for given cation, more the ionic mobility. As I have shown you in the table also, the ion which have more equivalent conductance, that have more ionic mobility as well. So if we replace this proportionality sign, then one constant is here, and that constant is the basically Faraday's constant. Means these two are something related with the charge basically. So F into UC. So you can write lambda C for cation. C here I am using for cation. C for cation, and I will use A for anion, right? So this is equation 1. Similarly, you can write lambda A is equal to F into UA. This is equation 2, right? So at any moment of time, if you divide these two equations, so you will get lambda C by lambda A is equal to UC by UA. If we add +1 on both the sides of this, see equation 1 by 2, right? So we get lambda A plus lambda C by lambda A is equal to U C plus UA by UA. If we reciprocate this, so we can write here lambda A by lambda A plus lambda C is equal to UA over UC plus UA. So this is a very important relation. Equation 3, right? So if you see, so both the sides are dimensionless. This is the fraction of equivalent conductance shown by the what? Anion, and this is the fraction of ionic mobility shown by the anion, right? So these two are the fraction. So one more term here we are using, that is the transport number. Transport number. As you know, this name itself indicating transport number means this has no unit. So transport number. So transport number is defined as the fraction of current transported by cation or anion, right? Cation or anion, that is called the transport number of cation and anion. And if you want to the complete transport number, so this is always equal to 1, because you know this is a fraction and sum of fraction is always equal to 1. So transported by cation or anion is known as transport number of cation and anion respectively. So transport number of cation plus transport number of anion, this is always equal to 1. Now see, transport number of anion is equal to ionic mobility. This is equal to the ionic mobility UA by the ionic mobility of anion plus ionic mobility of cation, and this is equal to lambda of anion by lambda of anion plus lambda of cation. So this is equal to, you can write lambda of anion by lambda infinite. See, this is the transport number. Now you have the relation between transport number and equivalent conductance. See, this is the equivalent conductance of AB and this is the equivalent conductance of what? Anion. Similarly, you can find the relation between T of cation. So T of cation is equal to U of cation by U of anion plus U of cation. So this is equal to lambda of cation by lambda of cation plus lambda of anion, and this is equal to lambda of cation by molar conductance of AB. So these are the different relations, equation 4 and equation 5. So now you can see that your all technical terms like transport number, like ionic mobility, they are converted into in terms of this equivalent conductance. So if molar conductance somebody asks are given, then you can convert this into the equivalent conductance. You have direct formula. But here equivalent conductance I preferred because you know this equivalent conductance has no problem with the number of moles which we are getting from the dissociation of electrolyte. That's why I have preferred here equivalent conductance. Okay, although IUPAC system ignores this term, right? But it is easy for you people. Okay, so this is all about this conductance and everything about conductance. Now conductometric titration, like acid-base titration, you are doing acid-base titration. So in acid-base titration, to detect the end point, you have to use some indicator. And those indicators are said to be acid-base indicator, and obviously indicators are also some weak acid or weak bases. So likewise, acid-base titration, you can detect end point by the measurement of their molar conductance or equivalent conductance. So this is called conductometric titrations. Conductometric titrations, right? Now see, conductometric titrations can be used for not only for acid-base titration, means to detect the end point in acid-base reaction. In any kind of precipitation reactions also you can use this conductometric titration. So basically, by conductometric titration, how to detect the end point, right? So we determine the end point. What is the meaning of end point? The meaning of end point is the milliequivalent of acid is equal to the milliequivalence of base. Right? So this is the meaning of end point. So we determine the end point by the measurement of molar conductance, equivalent conductance. Right? So this is very accurate method and more precise than the traditional method in which we are using this acid-base indicators. So first case I am taking here, titration of HCl versus NaOH. See, all of you should try to understand because students are always confused in this, but hopefully all of you are not will not confuse, because you have sufficient information so that you can understand it very easily. So see uh, how your this experimental setup, that also understanding of that also is very important. Otherwise if you see the graph in your book or anywhere and directly you try to understand that graph, you cannot understand that graph, what is happening there. So to understand this science, many times it is required to understand the setup of experiment, then only you can very easily understand. See, in this case, I am considering that whatsoever the this HCl is I am taking in the beaker, right? So whatsoever the normality and molarity of this, that hardly matters for us, because we are going to measure the molar conductance. But whatsoever the molarity normality is given, and we are adding in this beaker NaOH drop by drop, right? So NaOH is in burette, basically it is in burette. So the experimental setup is also very important for your understanding, right? So you have to take NaOH here. This is the stand, like this. So NaOH. Okay. Now see, when you add this, you have excess of HCl. So HCl solution, this is fully dissociated, strong electrolyte. When you add a small quantity of NaOH, NaOH is also a strong, electrolyte. So you have to understand what is the state of NaOH. NaOH is also dissociated. Now, when you add this quantity is in the limiting amount, so what change is taking place inside the beaker, you have to visualize that. So there is no change with the state of Na plus before and after, because whatsoever the state of Na plus is here, after mixing that will that state also exists, because before mixing it is present in the aqueous solution, after mixing it is present in the aqueous solution. There is no change in the state, because there is no bond formation between Na plus and Cl minus. This Na plus and Cl minus, they will enjoy freely in the solution. There is no interaction between them. There is no precipitation reaction, right? So Na plus and Cl minus, there is no change in the state of Na plus and Cl minus before and after mixing, right? But one change is taking place here, that H2O formation will take place. Means H plus from this HCl and OH minus from NaOH, they will combine and form water. And the molar conductance of H plus is the highest, and second highest molar conductance is for OH minus. So if H minus and OH minus continuously decreasing in the solution when you added NaOH in HCl, then what will happen? Definitely molar conductance or equivalent conductance will decrease with time. Right? And if you keep on adding this NaOH, at one stage there is equivalence point, means quantity of this and quantity of this are equal. After that, if you keep on adding NaOH, then what will happen? So molar conductance will continuously decreasing, sharply decreasing, because H plus is moving and Na plus is replacing H plus. So and OH minus, see, OH minus is also moving from out from. So only see the change here in the state of this beaker, that we are measuring the molar conductance of this beaker. So H plus is moving, Na plus is coming, and OH minus, whatsoever we are added, that is immediately converted into what, water. So there is no contribution of OH minus. So a large decrease in molar conductance we will observe, because you know the molar conductance of H plus is much higher than Na plus, right? And don't think about OH minus, because OH minus whatever is coming, that immediately converted into the H2O. So this is the change. So you will get, suppose that if we plot, if we plot molar conductance of this HCl solution, of this solution, versus volume of NaOH, volume of NaOH. So what we get? We will get the sharp decrease in the molar conductance, and after that there is a sharp increase. But this time the slope of this is may have some difference than this slope, and this is the equivalence point. This is the equivalence point. So the molar conductance corresponding to this is the equivalence point, right? Very simple. If you have ability to analyze the molar conductance of the individual ions, then you can very easily explain this. Now I am taking so this is HCl versus NaOH, or strong acid versus strong base. Any strong base, any strong acid. Shape will be this, slope will be the different. Suppose that you have taken diprotic acid or that base, different strength acid or base, but shape will be this. First decrease and then increase, right? But what will happen if NaOH is taken here and HCl you are adding from outside? Then the shape is this, but slope definitely will be differs greatly, because you know H plus and OH minus also have significant difference in their conductivities. Now the second case, if we take acetic acid CH3COOH plus NaOH. So this is in beaker, and this is in burette. Now see what will happen, which type of graph we will get. See, CH3COOH, this will a weak electrolyte and equilibrium largely shifted in the backward. So this is there and H plus is there, right? Very some H plus is there, equilibrium is shifted here. So you have to the knowledge of equilibrium, how equilibrium is shifted here and there, means left and right. And when you are adding NaOH here, which is a strong electrolyte, then what will happen? This OH minus will combines with this H plus and produces water, right? So what will happen, since this reaction is under equilibrium, so more acetic acid will dissociate to maintain the equilibrium as per the Le Chatelier's principle. So what will happen? So means if it is asked, okay, are you adding OH minus here in the solution? The answer is no, because whatever OH minus you are adding in the solution, that will immediately convert into the H2O, means you are doing nothing. You are not adding OH minus. So you are adding Na plus. So since Na plus is continuously we are adding, so the molar conductance will increase with what time? Means with every drop of NaOH, this molar conductance will increase. But the slope is not sharp as here increase or decrease, I mean the molar conductance. So in a weak acid and strong base, you will get this type of plot. Molar conductance and volume of NaOH. Volume of NaOH. So first there will be increase See, it is not a straight basically. Yes. So first there is an increase, and after the equivalence point, when you are keep on adding this NaOH, now after complete reaction with this acetic acid, what will happen? This will, I mean, this will sharply increase, right? So this type of plot you will get, and this is the equivalence point. Right. So this type of plot you will get for weak acid and strong base. Right. Clear? Now I am taking third category, HCl versus NH4OH. So HCl again in the beaker. So HCl, it is a fully dissociated H plus and Cl minus, and you are adding NH4OH. So this NH4OH is a weak electrolyte, so this will form the equilibrium like this, NH4 plus OH minus. So in this case, whenever you are adding this NH4OH in this solution, this will act as a strong, because you know, if we reverse this, that we take in beaker this NH4OH and we are adding HCl, then we will get the same graph as ever, right? But see here, if you are adding one drop here in this, this is in beaker. So if you add one drop of this NH4OH, this will act as a strong, no problem. But virtually you are not adding OH minus here, because this OH minus will immediately combines with this H plus and produces water. So this will produces water, means you are adding what NH4 plus. Basically, you are adding NH4 plus, but since this H plus is moving out and you are adding NH4 plus, and see the huge difference in the molar conductance in H plus and OH minus NH4 plus. H plus is 349 and where the NH4 plus 73. So you will get what? Sharp decrease in the molar conductance. Sharp decrease in the molar conductance. So if you plot molar conductance on this and volume of NH4OH, so decrease, and after that little bit increase, and you can say constant type graph we will get. Why? Because you know NH4OH is if you are keep on adding, that is I mean the weak electrolyte and make the equilibrium. So after some time it becomes constant. So this is the end point here. End point. So see here all skill of your ionic equilibrium is used. If you have no idea about what is equilibrium, what is Le-Chatelier's principle, how they are affected, so you cannot understand all these things, right? So this is HCl versus, and if you take NH4OH in the beaker and you are adding HCl, so you will get this kind of similar kind of graph, right? So be careful what is added in which. That is important. Now one more graph, and after that all of you should what do yourself, analyze yourself, and if you have difficulty, then we will discuss. Now, see, suppose that if we have KCl and AgNO3 and KCl. See, this is a precipitation reaction. Precipitation titration. Right? Now see, suppose that we have silver nitrate in the beaker, because first you have to define system, and you are adding KCl. So you know this silver nitrate is a strong electrolyte, and this will always be fully dissociated, Ag plus plus NO3 minus. And you are adding KCl, that is also a strong electrolyte here. So what is happening, this Cl minus will immediately combine with Ag plus and make the precipitate of AgCl, means this ion Ag plus ion and Cl minus ion, they are out from the conductance, means there is I mean no contribution of this AgCl in the what conductance. So what you are doing, you are replacing Ag plus and putting K plus. So see here, K plus and Ag plus, what is the molar conductance or equivalent conductance? If we have Ag plus, I do not have the Ag plus data. So I mean and Cl minus I have, but K plus I have 73. So okay, no problem. So what is the change here? The change is that Ag plus is moving, K plus is coming. So both have very close value of their molar conductance, not much difference. So if you plot this graph, here molar conductance and here volume of KCl, volume of KCl. So you will get what? Almost constant, because there is no much difference in the molar conductance of these two, K plus and Ag plus C. K plus is adding here and Ag plus is removing, and after equivalence point you will get the increase because there is no precipitation and only you are adding KCl, so the KCl will increase. So this is the end point of this. End point, right? So this is the way how to determine the end point in different types of titrations. Now in different combination you will do yourself. You have data and you have now a skill how to interpret these graphs. Okay. Now see, this is the last question I am considering here, and this is the end of your electrochemistry, right? So see, the specific conductance of pure water sample is this, as we have discussed in previous question also. And here lambda H plus is given, lambda OH minus is given, calculate the Kw format. So in a very simple way you can calculate this. You know, water is a very weak electrolyte and it is feebly ionized like sparingly soluble salts H plus plus OH minus, and you know, you can consider this like the sparingly soluble salt, that the concentration of ions means you can consider this as solubility, right? And you know, Kw is equivalent to the Ksp of sparingly soluble salts, which is equal to the concentration of H plus into concentration of OH minus, right? So if you are able to find out this concentration of H plus and concentration of OH minus, you very easily you can get the Kw value, right? Now see, molar conductance of water at infinite dilution, obviously that is due to the ions which are present at that temperature 25 degrees Celsius. This is equal to the lambda infinite of H plus plus lambda infinite of OH minus. Don't be confused that I am writing here lambda infinite means water is 100% dissociated. No, not like that. You have to consider this like a sparingly soluble salt, that whatsoever the maximum dissociation can take place at 25 degrees Celsius, that is there, and I am considering that is the maximum value. So that is lambda infinite. Don't be confused here. Okay. Now this is equal to 349.8 plus 198.5, right? So this is and now we can use this formula. S is equal to concentration of H plus is equal to the concentration of OH minus. This is equal to kappa into 1000 by molar conductance at infinite dilution for water, right? So kappa is given, that is 6 into 10 power minus 8 divided by this 349 into 1000 divided by this 349.8 plus 198.5. Now you can solve this, and this will come to 1.003 into 10 to the power minus 7 moles per liter, right? And now Kw is equal to concentration of H plus into the concentration of OH minus. So this is equal to 1.003 into 10 power minus 7 multiplied by 1.003 into 10 power minus 7. So this is equal to, you can write 1.00 into 10 power minus 14 mole square per liter square, right? So this is the answer, and this is the value also what we are using in the calculation of pH, right? Okay, so with this, dear students, your electrochemistry now complete. Okay.